In this video we'll be discussing comparing fractions and equivalent fractions. If you're trying to compare two fractions, it's pretty easy when you have the same denominator. Remember, the denominator is the size of the pieces. So if they're both the same size, you really just have to look at the numerator to decide which one is bigger. If you have 5/8, it's going to be larger than if you have 3/8. The way we read this statement is that 3/8 is less than 5/8. Hopefully you understand the three signs that we use to show comparisons between one part of a sentence and another. This is the less than sign. Lots of different ways to remember it. The way I remember it is the small part of the sign always points towards the smallest value. The larger part of the sign is in the direction of the larger value. That's why you see it here. That's the larger one to point towards the smaller one. If you turn it around and you put the 5/8 over here, then the 5/8 would be, this is the greater than sign. And again, the point would point towards the smaller one and the open end towards the larger one. This is the equal sign. It means that both of them are of equal value. When you have fractions that have different denominators, well, that sets up a whole different situation. And first of all, we're going to start off with just using maybe a little bit of common sense about fractions to try to figure out which one of these two in particular is the largest. We're comparing 11/12 to 19/20, and I've already put the answer in here. 11/12 is less than 19/20, and the question is why? Well, let's think about this, and this is important. It always takes the same amount, top and bottom, to equal 1. If you have 12ths, and you have all 12 of them, you have the whole thing. Same thing with 20ths, or any denominator for that matter. If you have 20ths, and the top number is 20, that means that all of the 20ths are present, so you have the whole thing. In these two fractions, you'll notice that you're one piece short of the whole. This is 1/12 short of the whole, and this is 1/20 short of the whole. So we're just using a little bit of common sense here. Obviously, this 1/20 are smaller pieces. If you break a hole into 20 pieces, it's going to be smaller than if you break a hole into 12 pieces. So that means that the 19/20 is one smaller piece short of the whole, which would make it overall a larger fraction. Okay, this is an illustration that shows that in the top bar we have a whole bar, we have a whole bar at the bottom that represent the whole. This one has 19/20 shaded in. This one has 11/12 shaded in. And you can see by the line that goes straight through the last 12th, this is the 11/12 mark, that when it cuts through the 20ths at the top, there's still a little bit of extra of the last 20th left over. That makes this overall section larger than this. So it proves 19/20 are larger than 11/12. Okay, here's another question. Why is 1/4 greater than 1/9? And here again we'll apply a little bit of common sense and also help with reviewing our understanding of fractions. If you break a whole circle, okay, the circle represents one whole, into 4 equal pieces called fourths, those pieces are going to be larger than if you would take the same size circle, representing one whole, and splitting it into 9ths, 9 equal pieces. Stands to reason that when you're dividing something just into 4, it's going to be larger than when you're doing it equally into 9 pieces. So a 4th is definitely bigger than a 9th. And the clue would be that denominator. This is 4 parts, this is 9 parts, more parts, smaller pieces. Okay, here's a question. Why is 5/9 greater than 12/24? Well, it's pretty hard to tell unless you look at a little trick and apply a little common sense here. The trick would be, think about 1/2 in this particular case anyway. And isn't this larger than a half? Where this is equal to a half. Now, how do we know that? Well, 12 is exactly half of 24. So that represents half of 24. So in a simpler form, that would be the same thing as 1/2. However, 5 is a little bit larger than half of 9. Actually, it takes 4.5 to make 9, 4.5. So this is larger than a half. And this is exactly a half. And that makes that fraction larger. Now, based on what we said, do you see why 7/8 is less than 20/21? Okay, what would apply? The fact that they're each one fractional piece smaller than the whole, and 1/21 is certainly smaller than 1/8. More pieces, smaller pieces. So therefore, the 20/21 is closer to a whole. Next, let's talk a little bit about equivalent fractions. Equivalent fractions are fractions that cover the same area of a whole, but they use different size pieces. The denominator is different. So in order to make up for the difference, for instance, you can see that this red section represents 3/5 of the entire bar. The same fractional area, can be shown if we change the pieces to tenths. Well, what happens when you change the pieces to tenths? Well, obviously you have 10 pieces in the whole. The pieces get smaller, and you can see that a tenth is exactly half as big as a fifth. Another way of looking at it would be 1/5 equals 2/10. So you can use tenths to equal the same area, but you must use more of them. And there's a mathematical trick to it, and we'll talk about that in a second. What if you took the fifths and split them into 3 sections? Each fifth now is 3 little parts. You can see that each fifth equals 3 of those parts. Well, these parts happen to be 15ths. We can tell because there are 15 of them in the whole. So what was taken up by 3/5 can be changed to tenths, and the same area will be covered by 6/10, can be changed to 15ths, and the same area would be 9/15. We change to 20ths, it would require, of course, that we have more of them to equal 3/5, so it would take 12/20 to equal 3/5. Let's talk more about this. There you see they're equal. They take up the same amount of space in the bar. Well, matching multiples. Here are those fractions that we just had. And that's exactly what we have. There is a multiple relationship between this first fraction, which is in the simplest form that it can possibly be in, and the other fractions that were equivalent or equal to it. You'll notice that the denominator goes by multiples of 5. In other words, the next number is the next number in the 5's place. So we have 5 times 2 equals 10, and the top number times 2 equals 6. So we've kept a multiple relationship. We've jumped one multiple of 5 and one multiple of 3. Here's our new fraction, and it's equivalent. Now if we were to jump times 3, we would go from 5 times 3 to 15, and of course 3 times 3 to 9. Here makes our new fraction, smaller pieces, more of them, to make sure that they stay equal to the larger pieces. And that last step that we saw on the previous illustration, times 4, this would be the next multiple of 5, 5, 10, 15, 20. 5 times 4 is 20. 3, 6, 9, 12. 3 times 4 is 12. And of course these multiples go on and on and on. We talk about infinity, multiples go on forever, as far as we know. And so consequently, if you will match the multiple at the top in the numerator to the multiple in the denominator, you can keep equivalent fractions going on endlessly. Now we can use equivalent fractions to compare sizes. For instance, if we took these two, we can't use the little common sense clues that we used previously. Those were good to think about fractions and what they mean, but it would be very difficult to use them here. We're not dealing with just 1/14 and 1/10. That would make it an easy problem. We're not dealing with a situation where the numerator is 1 less than the denominator, so it's 1 short of the whole in either one of these cases. And both of them are greater than a half. 7 is more than half of 10, and 9, hopefully we know that, is more than half of 14, because it takes 7 to make half of 14. So all those little tricks, common sense applications, don't work here. But what will work is if we can make these into equivalent fractions and then eventually get them to have the same size denominator. Let's see how that's done. Okay, here's the two fractions. Now we're going to start to make an equivalent fraction list. And if you remember how it was done on the previous slide, we're going to multiply the starting number by 2 in both cases. So let's see what happens. If we multiply 9 by 2, we go to 18. 14 by 2, we go to 28. We've made these pieces smaller by a half. Now we have twice as many of them to stay equal. We do the same thing with 7/10 times 2 gets us to 20. We've changed from tenths to 20ths, and instead of having 7, we now have 14 to stay equal. Now we haven't yet matched the denominator. Once we match the denominator, as we said at the very beginning, it's easy to tell which one is bigger. Okay, so we have to continue on till we can match. There'll be a different way of doing this later on when you get into a more advanced grade, but now this is the best way to do it. Okay, so moving on, we're up into a much higher number here. That means the pieces are getting smaller. This is the third multiple of 14. You might have to get a piece of paper out and do it because it is a large number. But 3 times 4 is 12, and when you carry the 1 and hold it, 3 times 1 is 3 plus 1 is 4. So that's 42, and if you know your nines table, 9 times 3 is 27. Well, we're kind of behind here. We're going to have to catch up. So let's multiply both of these by 3. 3 times 7 is 21. 3 times 10 is 30. We still aren't matching any denominators. We're kind of close here, but close doesn't count. They have to be exactly the same, so that we're comparing the same size fractional pieces. Well, let's go on. Okay, I still haven't reached the 42. I'm close again in size. 40ths and 42nds are very close in their size, but they're not the same, so it's really not good enough to compare yet. Okay, moving on. You know, this is the times 5. This is the 5th multiple of 10. 10 times 5 is 50. 7 times 5 is 35. So we're moving right along the line, yet we haven't matched yet. At the top, if we continue, we can be counting by 9s is one way of doing it. Counting by 14s. Or we can just use multiplication and skip all the way up here. 4 times 14 is 56. 4 times 9 is 36. Still haven't matched. Okay, well, let's just keep on going. Okay, the next multiple in the line of equivalent fractions would be the 6th multiple of both the numerator and the denominator. That brings us to 42 in the numerator. But we keep on going, and eventually you can see what happened. We have matched the denominators. We've changed 7/10 through all these steps to 49/70ths. And we've changed 9/14 through the series of equivalent fractions to 45/70ths. And now we can easily see which one is largest, and they're quite close in size. But when changed to 70ths, it proves that the 7/10 is a bit larger. It's 4/70ths larger than this one, 9/14.